Hello everybody, my name is Halo. Welcome to this video series where we are solving Codeforces problems in Python. We are doing the A to OJ ladder and we have entered level 2. We're going to be doing problem 227b today, which is called as effective approach. This is a tricky problem because, well, you can do a solution quite easily, but that solution will be exceeding the time limit and it won't be an efficient solution or an effective approach as they like to call it. So we have to go ahead and think in a way that we can find an effective solution for this particular problem. Let's just go ahead and see how we're going to solve it. Okay, so let's go ahead and read through this problem. This is a very big problem to read. I mean, that's how it is as the levels go on, but let's try to break it down to the best of our abilities. So once at a team training, Vasya, Petya and Sasha got a problem on implementing linear search in an array. According to the boys, linear search works as follows. The array elements in a pre-selected order are in turn compared with the number that you need to find. Okay. Once you find the array element that is equal to the required one, the search ends. Okay. So let's say you have some predefined order. So that can be something like 3, 1, 2, 4. You're going to be searching for the number 2. What they're saying is this will start from this element 3 and they'll keep going until it encounters that particular key, then it will stop. That is how linear search works, and that's what they mean by these two lines. The efficiency of this algorithm is the number of performed comparisons. The fewer the comparisons the linear search is made, the more effective it is. What they're saying is, let's say there's something like 3, 1, 2, 4, and you need to find out this particular value, 3 here. So 3 will be the first comparison that you make because firstly you look at the first index, correct? So in that particular case, there's only one comparison made. That means it is very efficient. But let's take another case. Let's say we're looking at this element 4. So we'll look at 3 first, then we'll move on to 1, then we'll move on to 2, then we'll move on to 4. That means it'll take 4 computations, which is the number of elements there are, n elements. So if there are 1 million, 2 million, 10 million, 1 billion elements, in that particular case, this will not be efficient if you're going to look at the last element or something like that. That is what we look at time complexity. We call linear search O of n because there will be n comparisons in the worst case. That's what they mean by all of these lines. Vasya believes that a linear search would work better if sequentially it iterates through the elements starting with the first one like this. Okay, in this problem we consider the elements of the array to be indexed from 1 to n, not 0 to n. In Python we do 0 to n minus 1. Here we're going to be doing 1 to n. That means we're just going to be adding plus 1 to whatever indexes we find to put the answer. That's it. That means. And ending with the nth one. That's it. So, and Petya says that Vasya is wrong. Petya says that Vasya is wrong. The search will need less comparisons if it sequentially iterates the element starting from the nth element and ending with the first one. So, even in this case, let's say this is Petya's approach. Sorry, this is Vasya's approach. And then this is Petya's approach. In Petya's approach, what he's saying, we'll start with this element right here, then we'll go in reverse order. Correct? So in this particular case, yes, 4 is the first element, therefore he'll be good. But if he gets 3, in that particular case, Petya's approach will be bad, but Vasya's approach will be good. So that is the problem that we are posed. We are supposed to find out which approach is better. So to finally begin the task, the teammates decided to settle this debate and compare the two approaches as on an example. For this, they took an array that is a permutation of integers from 1 to n and generated m queries of the form find element with value b1 in the array. So m queries of the form find element value b1 in the array. They want to, sorry, bi, this is not b1. They want to calculate for both approaches how many comparisons in the total linear search will need to respond to all queries. Okay, how many comparisons for all the queries? If the first search needs fewer comparisons, then the winner of the dispute is Vasya. If the second one does, then the winner is Petya. So there are two approaches. We know that the first approach is going from start to end. Second approach is going from end to start. So in the first approach, if this has the lower index value, or if this number of computations that we have to do is lower, that means Vasya will win. Sorry, Vasya will win. If not, Petya will win. We'll go ahead and work all of this out. You don't have to worry about that. So both approaches make the same number of comparisons. Then Sasha got the upper hand. But the problem is linear search is too slow. That's why the boys aren't going to find out who is right before the end of the training unless you come in here. help them determine who will win the dispute. I mean, again, they're giving you a clue that linear search is too slow. Okay, so we should not implement a linear search for the solution. I'll kind of explain as to why shouldn't do that as well. Before that, let's just look at how the input will look like for this particular problem. They're saying the first line contains an integer n, which is the number of elements in the array. Then it contains n distinct space separated. This word distinct is very important. That means that for every element, there will be only one index value. It cannot be duplicated. Okay, and the elements of the array is what we've got. Then we get a third line which has an integer m, which will denote the number of queries. Queries means some element e. We're going to find out what is the element of, index of this particular element e from Vasya's point of view, from Petya's point of view. Whichever is lower, we are going to give a point to them. That's it. Note that the queries can repeat. So these queries can also repeat. And they're saying this particular value is 10 power 5. This input n is also 10 power 5. Now, think about it this way. You are going to have 10 power 5 elements. Okay. So, let's just say an approach will be, I have something like 3, 1, 2, 4, 5, 6, 7. What I'll do is, I'll take, say my query has number 4. I will take this 4 value right here. I will perform a linear search to find out at what element, what index 4 is that. So we can do something like list.index of 4. This will give us the element. And give us the index of that element, sorry. And similarly, we can do the Petya side. So one thing we can clear now itself is this is Vasya's side. This is Petya's side. Okay. So instead of searching from backward, what we can do for Petya's side is we can take the same index value and then subtract it from n. That's all. This index will obviously give from 0 to n minus 1. So we'll have to add one plus 1 over here. Then if we do n minus this value, we'll get the side from Petya. Okay. From Petya's side, it will be 1, 1, 2, 3, and 4. So that will be 7 minus 4 minus 1. So in this case, 1, 2, 3, 4, 4 minus 1. That's it. So that will be 4 again. That is how you do this. That is nothing but 7 minus 4 plus 1. This is the same thing that we're doing here. That is what that plus 1 means. I hope that is clear for you. Why we are doing that plus 1 is because we are indexing values from 1 to n and not 0 to n minus 1. Once that is clear, now we cannot do this list.index function or finding the element with linear search every time. And tell you that because let's say there are 10 power 5 elements in the list. Okay. And then let's say the 10 power 5th element. That is the 10,000, sorry, the 1 lakh. So let's say the 10 power 5th element is some element, say 77. Now there are 10 power 5 queries as well, and all of these queries can repeat. If all 10 power 5 queries are this particular value 77, that means, see, for one linear search, since this is the 10 power 5th element, I'm going to do 10 power 5 operations. Correct. Similarly, again, for 77 being called 10 power 5 times, I will do these 10 power 5 operations 10 power 5 times. So totally I'll be doing this 10 power 10 times, which is not at all feasible, as our computer can only do 10 power 8 operations per second. So this is a time limit exceeded problem, and that is why we need to find an alternate solution on how we are going to solve this problem. So let us go ahead and look at some inputs, then we look at how we're going to approach this particular problem. So in case number 1 right here, we have n is 2. There are 2 elements, 1 and 2. Then there is only one query, which is 1. 1 from Petya's side is first element. From Vasya's side, it's second element. Right. So we have to also go ahead and say print what is the output. Print 2 integers showing how many comparison Vasya's approach needs, how many comparison Petya's approaches needs. Separate these numbers by spaces. So in Vasya's approach, it only needs 1 comparison. In Petya's approach, it needs 2 comparisons. That's why it's 1, 2. Space separated. Now let's take the second case. So let's take the second case now. Instead of 1, 2, now it's 2, 1. Rest of it is same. M is 1 and we're going to be searching for 1. This one from Petya's side will be first element. From Vasya's side will be second element. Therefore, the answer will be 2 and 1. So let's go for more queries. We have n is equal to 3, 3, 1, 2. Then we have m, which is 3. We have 3 queries. And that queries are space separated integers again as a list. And those numbers are 1, 2 and 3. So we need to search each of these values right here. In the first case, 1 is the middle for both Vasya and Petya. So in one will be 2 comparisons for Vasya, one will also be 2 comparisons for Petya, then 2 will be 1 comparison for Petya, but it will be what? 1, 2, 3. We have to compare this, go here, go there. So it will be 3 comparisons for Vasya. 3 will be 1 comparison for Vasya, but 3 will be 1, 2, 3. 3 comparisons for Petya. Add all of this, you get 6 comparisons for Vasya, 6 comparisons for Petya. Therefore, the answer is 6, 6. Okay. Now, how are we going to effectively solve this problem without using linear search? See, these queries, these values don't matter to us, because whatever we do, right, whatever this query value is, I need to be giving a solution in O of 1 time. If I give the query, I need to find out what the index is beforehand, and I can do that because all of these integers in this particular array are distinct, which means if I can assign what value, what indexes for each of these particular values, I can automatically just call these particulars, whatever values I'm storing, I can just say, yes, this is what I'm going to do. And how I can do that? For example, I'm saying, let's have an integer array, say 312 again. I'm going to say first element is 3. Okay. Or what I'll do is, I'll make this better. So I'll say 3, this number right here, 3 is the first element. I'll say 1 is the second element and 2 is the third element. And I'm just going to close this particular value, right? I'm going to store 3 variables like this for each of the elements in my list. Now, regardless of the number of queries that I get, I can always just revert back to this table and find out what I'm getting. So instead of doing all these searches, I'll just say, okay, 1, 2, 3, I'll take 1. Okay, what is the value for 1? 1 says 2. Okay, 2 from Vasya side. This we can count all of this from Vasya side. For Petya side, we can just do n minus Vasya side. Okay, so that will be 2 comma n minus 2 plus 1. So that will be 3 minus 2 plus 1, again 2 here. Similarly, in the second case, I'll say, okay, the element is 2. Let me go ahead and search 2. 2 is 3 from Petya side, 1 from Vasya side. Then element is 3. Let me just go to this table again and search for 3. 3 is in the first place. That's it. And all of this will only take one comparison because I'm just accessing these values. I'm not searching for this value. This 3 is already there. I'll just say, what is the value I have for 3? I'm not going to search again and say, okay, let me just go to this part right here. Let me go to the next case. Let me go to the next case. Is this matching or not? So we are not doing this linear searching at all if we are storing it in something like a table. That's where a hash map or a dictionary will come into place. In Python, we use dictionaries for these exact things because the cost of searching an element is just O of 1. And this is what we need. We don't need O of n, because O of 1 into n will give you just O of n and not n square in this case. When then O of n into O of n will give you O of n square. Okay. So let's take a dictionary and let's iterate through all these elements. 3, 1, 2, 4, 5, something like that. Okay. What we'll do is, for I in range, this n, we'll say this will be now 0th index. So let's say this is an LST. Okay. Now LST of 0 will be 3 and this 0 will be the index. What I'll do is, I'll say d of LST of 0 will be, or LST of I will be I. If I just put this particular function, what will happen? Let's say this is my D dictionary. First case, LST of 0 is 3. We'll say 3 is 0. Okay. Then we'll say, okay, 1 is 1. Then 2 is 2. Then 4 is 3. Then 5 is 4. Okay, these are all the indexes and the elements. Okay, so I'm going to put this in this particular format. Now, if I need to search for any particular query, I can simply say, for example, my query says the number 3. I can just call d of 3 and that will give me the value 0. From there, I can just calculate what is this. All of this is from Vasya's point of view. I'll say what is Petya's point of view as well, and then keep adding both values and finally print it to the user. That's it. So instead of performing a linear search, we're going to be initializing all these values for indexes into a dictionary, and then we're going to just access all of that so that our time complexity becomes lower. Let's go ahead and see how this looks like in code. If you're able to understand how we're doing this, please go ahead and do so. If not, stick around for the code. Let's go ahead and see how all of this looks like in code. See, firstly, we have to go ahead and take n as input, correct? Then we'll go ahead and take list. So there'll be list of map of int comma input dot r strip dot split. Okay. Then we have to go ahead and take m as input, int of input. Then let's say we have to take the queries. So we can take queries, and that will also be space separated list. So int comma input dot r strip dot split. Okay. Now we have to go ahead and create a dictionary to keep track of all the indices of this particular list, that is LST. So let's create a dictionary called D. Then let's just loop over all the elements for I in range of n. We'll just go ahead and say that D of list of I will be nothing but I. This will be the index, and so we can say this as element list to index. So we can create all of this. Now we have to go ahead and service these queries. Before that, we can say let's keep 2 pointers. So Vasya will be 0 and then Petya will be 0 initial. Okay. Now let us go ahead and count all the queries and how and increase the number of searches they have to do for each, and increase the number of comparisons they have to do for each search. So how that will look like is for I in these queries. So for each query, what you'll do is you will take this D of I, and that will be the, okay, let me just put this as Q in queries. Now the index will be given by query, D of Q, correct? So now Vasya's index will be given by, see, 1 to n only we are seeing. So we have to do a +1 over here. So V will be D of Q +1. Now let's go ahead find Petya's index as well. That is given by P, which is nothing but n minus this particular index's value, or n minus 1 this particular Vasya's value. Okay. So let's just say n minus this D of Q. Okay. To explain how that looks like, let's say for example this D of Q is all of these values right here, 0, 1, 2, 3, 4. From Petya's side, this 0 will actually be 4. That is the maximum. So we have taken this particular values 3, 1, 2, 4, 5. Let me just see, yeah, this values right here. This is 0, right, which is 1 for Vasya, sure. So this right here is 0. This index is 0. For Vasya, it's 0 plus 1. That will be 1 comparison he has to make. But for Petya, it has to be 1, 2, 3, 4, 5. 5 comparisons. We know n is already equal to 5. So that n minus this index value will give you what? Petya's number of comparisons. So that is why we are doing n minus this D of Q. Okay. So this will also be number of comparisons that they are making. So then what I can do is, once I had all of these values, I'll go ahead and Vasya plus equal to V, and then I'll do Petya plus equal to P. Once all this loop is over, I'll just go ahead and print Vasya comma Petya. Right. I save this, I run all of this. You can see all the test cases have passed. Let me just go ahead and submit this code as well so that you know that it works. That's it for the solution, guys. I hope this helped you. I hope you're able to understand what we're trying to do here. Yeah, as you can see, the solution got accepted. That's it. It's a very easy solution, guys, but you have to think a bit. I mean, especially when you're trying to approach it a bit efficiently, we're going to be creating this dictionary where we're storing all of these indexes, and we could only do that because all of them were distinct. No element shares multiple indexes. That's the only reason why we could do this D right here. From there, we go ahead and find the index. Then we'll find the number of comparisons for each Vasya and Petya. Then we'll keep adding that to 2 particular variables, and finally we print the variable. I hope this video was helpful. If it was, hit that like button. If you have any alternative approaches or have any questions, let them know down in the comments. Thank you so much for watching. I'll see you in the next video. Until then, bye.